Welcome back. Happy Monday. We're back to summer today, apparently. Who knows, right? My yard is filled with so much mud right now. It's really quite remarkable. Yes. The joys of home ownership. That's what I'm experiencing today. So, agenda things. Quiz 3 due Wednesday. You should be able to answer most of the questions on the right, except for 2, which we were going to get to today. Homework 2 was due Friday. Not everyone has finished it yet, so I can't go over it as a group, but if you have specific questions about why an answer was wrong or if you were unable to solve something, please let me know and I'll be happy to go over it with you. We are going to have class on Wednesday. Initially, at the beginning of the semester, I had planned to be away, but I am going to be here. So we will all be here, but we will not be here next Monday, which is our fall break, that 2-day period that serves no real purpose except maybe we got caught up on laundry or something, right? What can you do with 2 days? I'm not really sure, but I will obey the schedule of classes and whatnot. I posted this morning, homework 3, that the due date on the website here had an error in it. It will be due a week from Friday, so you have the better part of 2 weeks to finish that on the 19th. This should be a continuation of homework 1. The idea is to take the item responses that you wrote about the scale development for and do something with them using CFA. Now, I don't care if CFA is the right model for your item responses. I'm assuming it's not, but that's all we know so far, so that's where we're going to start. So even if you have binary responses, it's fine. Do a CFA. So I am looking for a traditional results section. As I note here, there is a list of things that needs to be included as well as the point totals by which I'm assigning these things, but it should not be a list. It should be something like you would see in a manuscript. And you are able to use the example from example 4's write-up, as well as there's some examples in your textbook about how to phrase things. You are allowed to use my terminology and hit find and replace, but please don't make me see forgiveness anywhere in your thing, or I will get very cranky with you when I read it. Is that a deal? That's a good deal? Okay, except maybe whoever is working on stuff that has to do with morality or whatever, right? You know, if it's really a forgiveness state paper, that's okay. So let me know as you go through this if you have any questions on what to include. I will note that I'm asking you for a couple of different tables. You should be able to get tabular information out of your output files if you use SAS, Stata, SPSS, and so forth. I don't want you ever typing tables of numbers by hand, so let me make sure that you all know how to use text to columns. So here's an example. For instance, this is what your output file from M+ will look like. The information that you would need to make a table is going to be, say, right here. So you can start by copying that, open up Excel slowly as it thinks about it. And hit paste. Now when you do so, it doesn't readily understand that this is a table. But there is an easy way to make it that it does understand. Under the data heading right here, there is an option called text to columns. And you can tell it that it's either fixed with or that it's delimited. In this case, fixed with will work just fine. You hit next. It fills in where it thinks the breaks are in your text to align it into columns. If it gets it wrong, you can double click and remove it. Or if you decide you want more than one, you can add another one, for instance. It usually gets it right on the first try, or pretty close, and then when you hit finish, it's in tables. So you should never have to type any of these numbers. What you will have to do, though, is provide better loadings. So M+, zoom in here, sit P by. What would be a better heading for that set of estimates? Factor loadings, yes. So the word estimate is not helpful in conveying what it is the estimate of. So estimate is just fine for the name of the column, but you have to put in better labels than this. And so for something like this, I would say, positive factor loadings or something like that. Likewise, sit2, Maybe item 2 would be better, something like that. If the items are short enough, you might be able to get their content in there. That would be even better, but if not, at least giving the number of the items. So you don't have to do too much more than add some labels. Make sure that you're using consistent numbers of decimal places. So you won't need these last 2 columns. I'm not asking for them. You will need these 2. If you highlight the columns, go to Home. Under the General tab here, you can tell it that these are formatted as a number and pick the number of the decimal places that you use. That way it all appears uniform and it looks professional. So I'm asking for the unstandardized estimates, their standard errors, as well as the standardized estimates. So you'd have to put in, some other label here. And you can find those standardized estimates down here. There are examples of everything I'm asking you to do inside example 4, either in terms of text, code, or plots. So I'm going to open this up. So for instance, here's what a table would look like to report model fit. If you have lots of models, it's helpful to put them in a table rather than the text. Here's what a table of estimates would look like. So unstandardized and standardized solutions, estimate and standard error. You can feel free to borrow this as well. Factor model predictions. I am asking you for this one here. Provide and reference a factor response plot. That's this thing right here. So I'm looking to see at what point on your latent trait your predicted item responses go out of bounds. And I'm looking for you to see that and comment on it as well. So that's what a factor response plot is. It's this thing right here under factor model predictions. The other thing that I'm asking for that you haven't seen yet is a distribution of factor scores. In M+, this line right here, we'll save them to a file, but if you have all of the plot options on, that's what I had in my example, you should get all of the plots. If you are running this in a Mac, though, or on Linux, right, it doesn't work on that, they don't have plots, so you have to do it on Windows to get your plots. I can help you do that, but once you get your output, there is a menu called View Plots, and then histograms is the first option here. So then you can go into it and ask for a histogram of your factor scores. And then you end up with something that looks like this. So I had made these in example 4. That's how you do it, is to go through the menu. To the best of my knowledge, there's no code that you can write. You have to point and click your way through these things. But this is something I can help you with during office hours if need be. And I think that's about it. I will remind you that assignments have to be 3/4 complete to be accepted as a first draft, but they don't have to be perfect because you get to fix them. So I will try to get these back to you within a week or so, and then on the syllabus, homework 3 revisions will be due on November 9th. So that way you can fix it, turn it back in, and get all the points. When you do fix it, I ask that you use track changes so I can see exactly what you changed, and to leave my original comments in, that way I can see what I asked you to change. If you did what I asked, you get your points. If I forgot to ask for something, that's on me. Deal? All right. So any questions on homework 3 that I can help you with at this point? Okay, well let me know if you do, if you're not sure what data to use or other things here. I'm going to shut some of this stuff down. So what are we going to talk about today, folks? What's our current topic? Do you remember? IRT, IFA. So what does IRT stand for? Item response theory. It's no more a theory than anything else, though. Any model is a theory, if you want to put it that way. What does IFA stand for? Item factor analysis. They are the same thing. They are 2 different phrases used to refer to the same family of models. Historically, Those terms have been accompanied by specific choices in terms of estimation as well as specific ways of writing the model. But by the end of this unit, you will understand they are just rearrangements of the same set of ideas. The big catch, though, is highlighted on this slide number 4 here. CFA, as we just finished, is a linear model. We predict item responses as a linear function of a latent trait. Now we're going to predict item responses as a nonlinear function of a trait. So in CFA was to linear regression. IRT and IFA are to nonlinear kinds of regression, such as logistic, probit, count, and so forth. So that's the big catch. So to understand in a general way how these models differ, here are the 3 parts of any what is called a generalized model, more generally. Ized means some kind of prediction of a not normal outcome, something other than normal residuals. So the part that you know already is number 3 here, the linear predictor. That just means your model, whatever on the right side of the equation. So we're going to end up with something that looks like an intercept and something that looks like a slope, as well as another form of it when you write it as an IRT model instead. The 2 new parts, the link and the non-normal distribution. So we talked about specific examples of these for binary data. What is our friend for binary data for a link? Logit, and its cousin probit, right? What is a logit? Say it with me. The log of the odds of the probability of a 1. Yes, very good. What's a probit? Is the z-score. It's the z-score that goes with that probability. They both serve the same purpose on different numerical scales. Their purpose is to make the stuff on the right side of the equation predict an outcome that is continuous and unbounded. So a logit is a transformation of the outcome to be predicted, which in the case of binary data would be the probability of a 1. That solves the problem that a linear model must understand that probability cannot go above 1 and cannot go below 0. So the link makes that happen. When you back translate the link predicted outcome, meaning in logits, when you back translate that to probability, the probabilities stay reeled in as they should. So there's a couple pictures of this that we looked at. This one actually was generated, the plot on the left is a linear effective x predicting logit y. The plot on the right is that same set of predictions back translated into probability. So back translate, if you're writing more formally, is inverse link function. But I think of it as just moving backwards from where you started. Logits continue until infinity. The highest logit that you can have in M+ is actually 15, and the lowest is -15. But as you keep going in unit differences in logit, the difference in probability gets smaller and smaller and smaller as you close in on 0 or 1. So probabilities will never go out of bounds when you predict the logit instead of the probability. Same deal with probits. Okay. So that's a link. Questions on that? Okay, then the other part, we're saying that our item responses don't have to be normal. They can be some other known probability distribution. Do you remember what it's called for binary? Bernoulli, or a more general form of Bernoulli, also starts with a B. Binomial. Bernoulli is a special case of binomial when you have only two possible options. So in this case, we've got 2 things to worry about with respect to our items. The residuals in the model, how far off our item response is that's predicted from the real one, those residuals can't possibly be normal if you have a binary outcome, and they can't possibly have constant variance across all the levels of the prediction because the variance in binary outcomes is determined by the mean. It's the probability of a 1 times the probability of a 0. That's what the variance is. So you will have maximum variance for an outcome that is a 50-50 split, and minimum variance as you move away from that 50-50 split. So what's going to happen in our IFA and IRT models is that there is no more such thing as item error variance. The residual variance at the end of the CFA model, it's gone. It's not that we're assuming that our predictions are perfect. It's that once you know what the probability of a 1 is that's predicted by the model, you know what the error variance around it has to be. It's determined. When you're thinking in terms of the predicted logit or the predicted probit, oftentimes people will talk about error variance as being a specific number that's tied to those underlying distributions. So let me get this picture. This one right here. Slide 15. The idea that logits are continuous or probits are continuous then is depicted on the left, where we would say that the actual continuous outcome, the logit or the probit, has a variance of either 3.29 or 1, respectively. So you will see those numbers show up in formulas whenever you need to approximate the error variance with some kind of number, like to get back to total variance, but just know that they're arbitrary. They're just scaling constants. You can multiply anything in a probit scale by about 1.7, and you can end up with something in the logit scale. So in the world of IRT, these models that use probit are called ogive, but it really doesn't matter which one you pick. Computationally speaking, probit is harder because you have to integrate to figure out what the back-translated probability is, and that's why logits are the easier way to go. So probit was invented first. Somebody way smarter than I figured out that you can use logits to sort of cheat your way into probit, and then they started doing it that way. But this 1.7 will also show up when you read IRT textbooks or articles or documentation of IRT programs, and that's where it comes from, is the idea that you can change the scale of the model into logits or out of logits by a factor of 1.7. All right, how are we doing so far? So what we're going to be doing then, eventually, is factor analysis, confirmatory factor analysis, predicting logits or probits instead. That's where we're headed. That's the big picture. How to get there, though, has been a continual struggle in teaching this, because I like to start out with IRT in terms of how these models are written, because I like that version of the model much better. The parameters make a lot of intuitive sense, but it looks nothing like factor analysis. So we're going to start with IRT, but just believe me for now, you can algebraically rearrange the A's and B's I'm about to talk about into something that looks like intercepts and loadings. It really is the same model, just conveniently rearranged to give the parameters for the items more useful definitions. All right, are you ready? We're pumped, right? I've already had all of my ratio of coffee today, my regimen, so hoping the Sprite will do well enough to talk about logits. So, how this is the same as CFA. In CFA, we had person parameters and we had item parameters, right? Person parameter was what before? How do we describe each person in CFA models? I'll give you a hint. Is it the sum across items? No. That was classical test theory. How do we describe differences between people? What does each person get their own of in CFA? A factor score, right? Still happening that way. Now factor scores are thetas. So we're switching terminology, but it's the exact same idea. Items are going to get their own parameters as well. And depending on how you write the model, it's either A's and B's or loadings and intercept-like things. We still are assuming whatever dimensionality that you put into the model. So it is a common misconception that IRT models assume everything is unidimensional. They don't. It just turns out to be way more complicated to estimate them if it's not unidimensional, and so for that reason, historically, people have tried to make IRT models unidimensional, but they don't have to be. The idea is that whatever dimensionality you say the model has is what you assume. So if you fit 2 factors, you're saying it's bidimensional, or 2-dimensional. If you don't include any other kinds of relationships, such as error covariances or method factors, you're assuming something called local independence. That the only reason the item responses were related in the first place is because of your latent trait, is because of theta, and that's it. The catch is that in these models, when you're using full information maximum likelihood, which is what we use for CFA models, you cannot have error covariances. So you have to find other ways to incorporate additional sources of dimensionality besides error covariances. And it works out that you can use method factors for that. So the big difference then is this idea of the link. How this differs from CFA is that we're predicting a logit or a probit. So here's the same picture again, now with the y-axis labeled appropriately. So this picture on the left here shows the linear predictor. Beta 1 is the slope of my latent trait, and the prediction from theta to the logit of the probability of 1 is linear. So when you're talking about the outcome as being the logit or the probit, the link-transformed outcome, the model is in fact linear. When you talk about the prediction as predicting probability directly, the model is nonlinear. The slope shuts off as you get close to 0 and 1. Now this is still a specific kind of nonlinear. It's monotonic, which means that it goes in one direction, even though the slope slows down as you get towards the bottom or the top. But this is what's known as a parametric IRT model because it follows a specific S-shaped curve. So it's nonlinear, but it's a specific flavor of nonlinear. There are other kinds of models that allow different kinds of nonlinear or data estimated kinds of nonlinear, and those are called non-parametric IRT models. We don't have time for those, but they are out there. For instance, it may be the case that rather than your probability of a 1 increasing as a function of theta, at some point it decreases. So if it were to go up and come back down again, this model can't handle that. That's not all that typical, though. Typically you assume the more of the trait you have, the probability of a 1 is higher. So this could be the probability of a correct response or the probability of an endorsement, for instance, if you're saying, do you do this behavior or not? Now the names. So here is the organizational system by which you can think about what to call these models. There are 2 ways to estimate these models. There's full information and there's limited information. Full information means you use all of the original data. That's what we do by default most of the time. So you've heard of this in the context of missing data analysis, FIML, full information maximum likelihood. That is what's in SAS proc mixed, that's what's in M+, that's what we do in CFA, that's what we do almost all of the time when we have item responses or outcomes more generally that are normal, that the residuals are normal. So there's nothing new about that. When you combine that idea of full information maximum likelihood using all the original data with a specific way of writing these models, which include discriminations and difficulties, which we will get to today, then the world will call that IRT, that unique combination of full information and the way of writing the model that includes these discrimination and difficulty parameters. You can use that same type of model and estimate it in limited information instead. That means you are using a summary of the data. And the summary that you would use is what's known as a tetrachoric correlation matrix. Have you heard of this before? I think we talked about it some weeks back. Think of it as the correlation among the probits. That's the easiest way for me to think about it. We will talk more about estimation a little bit later on, but the big thing to remember is that this is way easier. Limited information is way easier because it is using a summary of the data instead of the original data. The other way that you can write these models to make them look a lot more like CFA models is with factor loadings and these other things that are called thresholds, which is -1 times an intercept. So when you select loadings and thresholds along with limited information estimation, the world calls this IFA. It is, of course, possible to select the off combinations, but to the best of my knowledge, there are not specific terms. So to hedge your bets, what I would always do is tell the reader exactly what choices you made. Don't just rely on them to know what these words mean. So in M+, the way M+ works is that it estimates the IFA model, the loadings and the thresholds directly, and then you can translate them into the IRT version of the model. So when I write this up, like in your example 5, I say I'm doing IFA because that's what's being estimated, but then you have to specify, are you using full information estimation or limited? And you would want to report not just that you're using M+, but what version, because these things continually get updated. Particularly between version 4 and 5, as I recall, WLSMV started giving different responses. So I'm starting here because I think the version of the model that goes with difficulty and discrimination, even though it looks strange, those two terms are way more intuitive to me than their corresponding terms in IFA. But they are really the same thing. You can get from one to the other. Are we ready? You're not looking very ready. We're ready. I'm deciding we're ready. Ta-da! So this is what we're doing. IFA models are almost always written predicting the logit, just like we saw earlier in this lecture last time, whereas IRT models are almost always written predicting probability. So that's part of the reason why these things look different, in addition to what they contain. So we're going to start with probability models right here, because that's the world how IRT tends to write them. Here's your very first IRT model. I wrote it both ways. So there are two new things in here related to each other most simply if you look at the logit version of the model. So the trade-off here in how to write these things, if you predict logits, it's the left-hand side of the equation that looks all complicated and the right-hand side is easy. If you predict probability, it's the opposite. So it's like, which one of these, where do you want your complexity, right? They're the same thing. So that term, let me get my happy little pointer here. This thing right here, this is theta. This is where our factor score used to be. So it's the most likely latent trait for each subject given their pattern of item response. The other thing, which is B, and this is an almost universally accepted terminology, B is item difficulty. And this time, it really is item difficulty. Because what's different about this equation than most regression type equations you've ever seen? Just this right here. What's different about this? I need a better pointer. What's different about this? What's in the middle? A minus sign. When was the last time you saw a linear model with a minus sign? Never, right? But these models are written with a minus sign. That way, item difficulty really is difficulty. A higher B means that you have a more difficult item and a lesser chance of getting it right. B's are referred to also as location parameters because they describe the item's location on a trait. So logits are somewhat hard to interpret, but you remember what a logit of 0 means, right? That's your benchmark? What's a logit of 0 correspond to in probability? Yeah, 50-50. So if you think about this, what we're going to do here is put people and items literally onto the same scale. And item difficulty is as difficult of an item as theta means as smart of a person. So if I have an item whose difficulty matches where I am on theta, my logit is 0, which means I have a 50-50 probability of getting it right. That is the definition of these item difficulty parameters, B. It's the point on theta where the probability of getting it right is 50-50. So if I am smarter than the item is difficult, my logit is positive, and I have a greater than 50-50 shot. Conversely, if the item is more difficult than I am smart, I have a less than 50-50 probability, a negative logit. So these are on the same metric. So if I told you that I had an item whose B value was 2, for instance, if my trait is distributed as a z-score, that means it takes somebody who has 2 standard deviations above the mean of ability to have a 50-50 shot at answering that correctly. And I can figure out, once I know what theta is and once I know what B is, what the probability would be for any combination of the 2. So this model has 2 names. According to IRT people, this is what's known as the 1PL, the one-parameter logistic model. The one parameter refers to how many item parameters there are, and in this case there's only one, there's B. Theta is in all of these models. In the notation, where we have the probability that y equals 1 and this bar here, this means given, theta. Theta is technically speaking a random effect, meaning that theta is not part of the model, but its distribution is. So that's why we have this bar theta here, whereas B is a fixed effect. Each item gets their own, and that is a model parameter. So the more items you have, the more item parameters you have to estimate. So one parameter logistic model, because we have one parameter per item, and we're predicting the logit. Not a terribly creative name, but it's descriptive. So if you're an IRT person, that's what you call this. The alternative is a completely different theoretical viewpoint, even though it's the same damn model. This is known as a Roche model. There's a whole tribe of people that are Roche people, and like literally, like it's IRT is voodoo. Roche is the way of the world, and it's a very different theoretical orientation. They believe that all items should be equally good, because you know that what's not in here? Any definition of item goodness. There's only item location. So we're going to have to add another letter to get differences between items and how well they work. So how to interpret these things is different than thinking about what a score means, because the interpretation is only relative to the scale of the overall model. So this is an idea called conjoint scaling, that people and items are on the same spot. They're on the same scale. So in classical test theory, or in any kind of typical norming development for a scale, you have to know what good means, right? So if Huey comes home from preschool and says, "Mommy, I got a 12." Out of how many? Like, is that good? Right? Is it 12 out of 12? Is it 12 out of 100? So I need to know like what the denominator is, or I need to have some sort of norm reference, such as I have a GRE score of 780, and my mom's like, "Is that good?" And I'm like, well, it put me into the 99th percentile. It must be pretty good, right? You have to have some outside comparison to know what these things mean. In the world of IRT, you don't need that. You only need to know how difficult the item is to know what it means. So let me give you an example of this from your textbook as well as from my own mind. So this is a working example of a construct map. We talked about these very briefly the first week of class, but the idea is that we have one side that's items and one side that are people. So this is my personal area of expertise, 80s pop culture. You don't ever want to play Trivial Pursuit with me on your team. I know nothing about literature, history, art, drama, sports, geography, science, nature. I'm trying to think of any of the categories. I don't know anything. I know like this stuff and 80s pop culture. So the pink category, I am solid in, but everything else you don't want me on your team. So to provide you with an illustration, let's say that I have a unidimensional trait of 80s pop culture. So at the bottom of the trait where things are easiest, if I said, do you know what the song Mickey goes like? Oh, Mickey, you're so fine, you blow my mind. Hey, Mickey, right? It was cheerleaders in the video. So even somebody like my mom, who's pretty weak on 80s pop culture, would know that reference. She was busy in the 80s raising children, wasn't paying attention to what was on the radio or MTV. I would say your average adult would be somebody who could be competent in naming all of the Cosby kids. Would anyone like to try? No Googling. Who was the youngest one? Rudy. Her older sister, next up, Vanessa. After that, the boy, Theo, yes, next. She got her own show, A Different World spinoff. Was married to Lenny Kravitz briefly, I believe. It was Lisa Bonet, remember her name? I'm blanking on it now, hang on. Theater, Denise, thank you. And then the older sister who popped up every now and again? No? Sandra. Yeah, see, this is the kind of thing that I retain, even though I know nothing that's useful, really. I would say that your average undergraduate who is sitting watching cable mindlessly and comes across this movie would know who the donger is. Any of you know that reference from a movie? Donger's here for 5 hours and he's got somebody. I live here my whole life and I'm like a disease. No? Nope, 16 Candles. The Donger was a very famous character from that movie. My brother once tried to stump me by asking me who the other person in Wham was besides George Michael. There was two guys. Do you remember the other one? Nope. Andrew Ridgeley. No one does. That's why this is a really difficult question that is probably worthy of someone like my brother's knowledge, but he's pretty good too. He knows a few more things than me. That's what the rest of the world says too, but no, it's Andrew Ridgeley. And then last but not least, there was a TV show, I'm going to go with 87-ish when it premiered, named Alf. And it was another like weird, I don't even know how to describe it. It was like a dude in a costume. It wasn't animated, more like the dinosaurs. What planet was Alf from? Does anyone remember? See, this is like the hardest question I could think of. This is like equal to my level of latent knowledge. He's from planet Melmac. See, all these things that you didn't know, right? But the point of this illustration is that you were able to follow me even though there are no numbers on this chart. The way that we interpret how smart a person is what they can do. What is the level of item at which they would have a good shot at solving it correctly? Yes? It's not how many questions you can answer. It depends on which questions you answered. It depends on the model. So in the Roche model, the number of questions that you get right is a sufficient statistic for your latent trait. And that causes some conveniences in estimation. But that's only because you would assume that all of the items are equally good indicators of the latent trait. If we augment the model to allow differences in discrimination, as it's going to be called, the relationship, the strength of relationship, then you have to know which items you got right because certain ones count more, essentially. So the model would assume that anybody who knows who Andrew Ridgely is has a greater probability of having answered all the things underneath it, and that they would have a lesser probability of knowing where Alf was from. So it's not a hard step function, but it is a curve. And I think I may have a curve either on the next slide or shortly thereafter. Yeah, not quite. It is a curve that looks like that. Get back. Nope, let me go back. So we'll get there in just a moment. But the key idea is this conjoint scaling thing. It's that the items difficulties have reference relative to the traits and vice versa. So when you're characterizing someone's trait, you're referencing it in terms of what it means as to what kind of item they would likely be successful at or not. Yeah.
So I understand how this works with reference to like knowledge, or with like personality. How do you have like a hard of
Think of it as severity. That you'd so give me an example of what you think a severe item would be. Sure.
Enjoying art, enjoying aesthetic beauty.
Okay. So you have to have a lot of openness to experience to want to get some art?
I really love doing that.
Yeah, so you can think of it in the same way it is severity. Like it's amount of the trait. How much of the trait does it take to endorse that item? What would be a low openness to experience? What's something that everybody likes? Wayne? Wham. My husband would disagree with you there. I think he would lose his will to live if I started playing Wham around the house. But how about maybe a new kind of pizza? You don't have to be very open to experience to try a new kind of pizza, right? Because there is no such thing as bad pizza. So that would be a low, I don't know, that's what I say. I would eat pizza every day of my life if I could and not die of scurvy or something. Although I wouldn't because I put pineapple on my pizza, so I'm covered. But that's a whole nother story. So yeah, the idea then is that would be a low difficulty, low severity item, pizza, because it doesn't take very much openness to endorse, yeah, I want some new pizza. But it would take a whole lot of openness to endorse, yes, I want to spend 2 days wandering around an art museum or something, right? I'm not that open. So somewhere between the two. So yeah, think of it as not just difficulty but severity. It's like how much of the trait does it take to agree to that item? Okay, your question?
Is it not simply like loading, because the higher the loading would give you higher factor score?
This is analogous to an intercept, not a loading. There's no loading in the model yet, which means that we're assuming the loading is actually the same across items. That's why it's a 1-parameter model as opposed to a 2-parameter model. That one's coming next. So giving you another example. This is from your textbook. Not your textbook. This is from Susan's book. I assigned you some of the chapters. So, for instance, if I gave some older adults a scale measuring functional independent living, basically activities of daily living, to what extent can you do these things either with help or without help? And let's say that the test yielded some sort of standard score, and we looked at this and we would say, well, this person right here is Vera. She's clearly doing the best. Anne is doing the worst, and these two are somewhere in the middle. But the fact that Vera is doing better than Anna does not tell me anything about what Vera can do, just that she's relatively better. An IRT example of scaling for something like this would put the people on the item metric. So if Vera got a theta estimate that was the same as the item difficulty value for this, then that means she has a 50-50 shot at being able to get out of the tub all by herself. That's her level of functional independent living. That's her latent trait. She has a less than 50-50 shot at being able to do stairs, because stairs are harder. She has a greater than 50-50 chance at being able to bathe or walk or do all of the rest of these things on the list. Anna down there, the worst one, she has a 50-50 shot at being able to groom herself, but anything above that would be less than 50-50. So you have to know the scale of the model, but then you can interpret the difficulty of the items, and that then informs what these scores for the people mean. So the theta estimates that you end up with are not determined by the exact items taken. Given pre-calibration, you can skip some items or add other new items, and that's the basis of adaptive testing, that you deliberately change the test for each person so that you give them only items that are relevant. So in this example, you might start somewhere in the middle and ask, okay, can you go to the bathroom by yourself? And if the person says yes, then you'd head this way. Okay, can you walk by yourself? And if they say yes, you keep going. If you know that they can walk by themselves, you don't have to ask if they have bladder control. You can save time by only administering items that are going to be relevant for narrowing in exactly where they are on this continuum. So this idea that you don't have to have the same items for each person can be leveraged to create an exceptionally sensitive test given pre-calibration of all of these things onto the same latent trait. The standard error, though, for theta is going to depend on the items. So what's going to happen in this example is that likely Paul and Mary here, their thetas would have lower standard errors than either Vera or Anna, because there are relatively few items at the extremes by which we could figure out exactly how able Vera is and exactly how unable Anna is. We don't know how low they are if we don't have enough low items. So in thinking about building a test within this framework, it's not just how good the items are, which is discrimination. That we haven't gotten to that yet. It's where they are. So if I wanted to build a screener for whether or not someone needs to go to a nursing home, I would want to fill up on these low-end items, because once you get to a certain point, if you can walk and bathe and all this stuff, then I know that you're going to be okay. Versus if I had a screener for whether or not you can participate in my new exercise program, I would want to load up on the high-end items to figure out exactly how able you are, because that's the people that I want precise measurement on. So in testing, one size may not fit all. You have to think about the purpose of your assessment and whether or not you want to measure certain types of people better than others, or whether you want to hit everybody across the board. The standard errors of these things are going to be dictated by those decisions. So to make this idea that we don't have discrimination differences in the model more explicit, I have added a letter out front, A. That A does not have an I subscript. That means that all items get the same A. So this idea that all items are equally good, we've heard this idea before, right? What's it called? You tested it at the end of your homework. Starts with a T. Tau equivalence, or a synonym for it? True score equivalence. That's what the Roche model makes, this 1PL. It assumes, without testing, it can be tested, but the model, this form of it, assumes that all items are equally discriminating. So this new A parameter is item discrimination. That's what it's called. It indicates the strength of the item's relationship to the latent trait. So when you're predicting a logit, this A is linear. When you're predicting probability, it becomes nonlinear. So in the probability space, these are the types of curves that that equation will generate. So I created equal discriminations here. I believe this is just a discrimination A of 1. And I varied item difficulty. So these are what's known as Item characteristic curves. These are very famous things in the world of IRT. They are abbreviated with the acronym ICC, not to be confused with intraclass correlation. This is an item characteristic curve. So I generated 4 of these curves for 4 different items. So the first item on to the last one to the left, let's go there, right here. This item curve was generated given a B value of -2. So what that means is that at a trait level of -2, which in this case the trait is z-scored, so mean 0, variance 1. So at -2 standard deviations on the trait, that is where this curve intersects with probability of 50-50. So this is a really easy item because it only takes -2 thetas to have a 50-50 shot, and it gets really, the probability of answering a 1 increases very steeply after that. The next item over has an item difficulty of -1, and that's where it hits 50-50, and here's 0 and here's 1. The fact that these curves are parallel is a consequence of the fact that they all share the same A parameter right now. They all are assumed to be equally discriminating. So this A parameter, when you think about it in probability, predicting probabilities, it is the slope of the line at the point of difficulty, at the location. So these are nonlinear slopes, right? The slope up here is very flat. The slope down here is very flat. It's the steepest at the point of inflection of the curve, which happens at the B value. So A is a measure of discrimination. It's an indication of how good the item is, how related it is to the trait, but specifically at the point of difficulty, at the point of B, at the location. This is a big difference because it controls if an item is good, who is it good for? All of these items are equally good in the sense that they have equal discriminations, but they're equally good at different ranges of the trait. This first item here with a B value of -2 is only going to be useful in differentiating people around that region. Once you get past, say, like a theta of 0 or so, that item is functionally unrelated to the trait. So B1 is not a good item for really high theta people. Likewise, B4 is not a good item for really low theta people. So previously in classical test theory, how do you make your test better? You get more items. What kind of items? More. That's it. And then CFA came along, and how do you make your test better? You get more good items. Where good means you have a strong factor loading, and if it's a strong loading, it's a strong loading for everyone because it's a linear model. So now we're adding beyond that. How do you get more items? Not only more good items, but more good items in the places where you have holes. The item has to be good in the region that you need it to be good for it to be useful to you. So not all items can be described simply as good or bad. It's good or bad for whom. And when you're thinking about building a short form, this matters just as much as discrimination, location. What you don't want to do is truncate the range of the test over which you have decent measurement. So you have to pay attention to not only which items are good, but where they're good at. So that foreshadows then the next addition to the model, changing single A to A with an I subscript. So this is called the two-parameter logistic model, because now each item is described by 2 parameters. Each item gets its own slope. So now, not only do items differ in where they're useful, their location, they are also allowed to differ in how useful they are at that location. That's A. So I think I have a picture next. Yeah. So this is the point where Roche people would say, we have committed voodoo, and they would stop listening. Unequal A's is against their religion. But here's a picture. This is slide 31. It's easiest to describe what these parameters mean in terms of pictures. So the first two items, B1 and B2 in blue, they share a common difficulty, the common location, a B. They both cross 50-50 at a trait level of -1. Likewise, these two pinky purple ones share a common B value of 0. They both cross the 50-50 mark at a trait level of 0. Within each one of them has a discrimination of 0.5, which is the flatter one, and one of them has a discrimination of 1 instead, which is the steeper. So if I were going to drop two of these items, the ones that I would want to drop are not both blues or both purples, but the shallower one of each. Steep is good. So you would want to make sure that you have items that spread all the way across the trait, and then within those, any that are redundant in terms of the areas that they cover, steep is better. Now, why do Roche people think this is voodoo? Because these curves, if you allow them to have different slopes, are eventually going to cross. And that violates something called specific objectivity. The idea that the items and the persons should have invariant ordering. So as an example of when this starts to break down, let's look at a theta of -1. Items 3 and 4, the purple items, are harder than the blue ones. They're harder because they have a lower probability of getting it right at the same level of theta. So blue is easier than purple. But if you follow these curves all the way up to +2, look what happens. It's no longer the case that purple is harder. This purple is actually easier than that blue. They got out of order. Yeah?
Isn't that just the interaction?
It is. It means that how useful the item is changes across the trait.
How does that buy it?
That Roche people won't buy that. That's just no. And what they would do is any item that had a different discrimination in practice would get thrown out. They would homogenize it. It's a philosophical difference that all items should be equal in terms of their discrimination. If you're making, say, math items where you're just swapping out numbers or something, I'll buy that. But any sort of attitudinal item, anything in the world of social science rather than educational science, it's really hard to make a test where all the items are equally good. So it's a philosophical difference. To me, it's something that I think it's an empirical question. Do you remember how in homework 2 and in our example we tested whether or not the items were tau equivalent? Remember that? We're going to do it again. You know how we're going to do it? Same way we did it before. Likelihood ratio test. -2 log likelihood difference. Empirical question. In programs like M+ that allow you to customize everything, you don't have to pick one or the other. It doesn't have to be the case that all items are different in terms of their loadings, their slopes, or all items are the same. If you had 1 or 2 items that looked really different than the others, you could let their slopes be different and then allow the others to all be the same. You could be like a 1.5 PL, essentially. You could do hybrid type models. It just depends on whether your software lets you. But yeah, because the ordering of the items in terms of their difficulty changes across the trait, that's what would blow up Roche people's heads. The rest of us just have to accept that if you allowed items to differ in their discrimination, that this is a consequence. All right. So we already answered this question on the next one, the idea of what goes into theta. If you fit a Roche model, if you fit a 1PL, this model, all you need to know is how many items you got right, and that's enough to compute a theta. If you fit this model instead, you have to know which items you got right, because the ones that are more discriminating essentially count more in trying to estimate your theta. Here's two other ones that I will not give you any examples of, but if you're in the world of education, you will see this. Guess what comes after a 2PL model? Can you guess? 3. What's better than 2? 3. Brings up a bit from Dennis Miller. He's speaking of 80s trivia. He used to talk about Kmart and how they'd have like buy one, get one free. Said, you know what, folks? 2 of shit is shit. If they really want to mess with you, they'll give you 3. Except his language is a little harsher. That's what I think of. 3. What's better than 2? 3. This is a C parameter. So we started with B, we picked up an A, and now we have a C. This is what's known as a lower asymptote. So basically, the model starts off with this constant C out front that is irrespective to theta. It just automatically bumps up the probability above 0. And then the rest of the model, the curve, is dictated by the amount of probability remaining after bumping that up. So it's known as guessing. So for instance, here's some pictures that differ in their C's. If you give a multiple choice test, you have a 0.25% chance of answering one of 4 choices correctly, right? Not all distractors are equal. So if you have an item where one of the distractors is really implausible, your chance of getting it right just from chance goes up to 0.33. So those are situations in which you would estimate a lower asymptote. For instance, this one is 0.2 on this item, or 0 on this one. So what that means is that regardless if you can be the dumbest person in the history of the world, your chance of getting this right is the lower asymptote. So it's the part of the item that has nothing to do with the trait that it's measuring because of some other characteristics, such as how easy it is the choices are to rule out, that kind of thing. So when you have a 3PL, the definition of these B's gets off from 50-50 because of this shift, but you can still think of them as location-type parameters. They're just not tied to 50-50 anymore. And one more. Can you guess what's coming after 3? 4! With the letter D, because why not? These people are super creative, let me tell you. D is an upper asymptote, and this is a relatively newer model. I haven't seen too many instances of it, but this is basically, you could be the smartest person in the world, and you have less than 100% chance of getting this item right. So it's thought of as a carelessness or a slippage sort of parameter. There's some examples in like the psychopathology literature, things where even people who are super high in psychopathology would not answer this. Like, on a scale of 1 to 5, how likely are you to go home and kill your spouse today? That kind of thing. Most people are going to recognize that maybe admitting to premeditated crime is not in their best interest. No matter how psychopathy? Crazy? Can I just say that? Can I just say crazy? I can't come up with the noun for it. So an item like that even if they are the craziest person in the history of the world, they still don't have a 100% probability of answering that question with a 1, for whatever reason. So you can fit, then, lower and upper asymptotes in differences in difficulty and discrimination. So I have M+ recently introduced these in their version 7.4. So the main ones we're going to focus on then is just this A and B. Go back to the picture with just those. A is the slope of the line at B. B is the trait level at which you have a 50-50 shot of answering it correctly or endorsing the item. That's what I want you to take home. The rest of this is new vocabulary. So do you remember what we called it when I said that you have to give your trait a scale, a mean and a variance? A special word starts with an I. Identification. Guess what identification is called in IRT? Anchoring. New word, same idea. The two options that you have to identify your model in M+ are the same if you're doing CFA or IFA. You can either fix the characteristics of your trait, set the mean to something, set the variance to something. 0 and 1 are very common, very helpful. Or you can fix the characteristics of one of your items. So you either set your factor variance to 1, your theta variance to 1, or you fixed one item's loading to 1. On the mean side, you either set the mean of your trait to 0, or you can set it's going to be an analog to difficulty to 0 instead. So something's got to be 0, something's got to be 1. It can be other numbers, but those are more common. So you already know how to do this. Same rules apply. Each trait needs to have a scale. The factor needs to have a mean and a variance. How many items do you think you need in IRT to have your model be estimable? 3. How many do you need for it to be testable? 4. Same rules apply. Now, something different. Reliability. Reliability we can still have, but it comes from a different place. It comes from something called test information. Test information is related to your item characteristic curves. So let me show you, while on a brief time here, what we have left, how this works in terms of CFA versus IFA, because I think understanding information will be helpful if you see it from this perspective first. So here is a CFA plot, like you're going to do in homework 3, where I took the unstandardized intercepts, the unstandardized loadings, and I made a picture to show you what it would look like. So they're linear. A 1-unit change in the trait creates the same change in the predicted item response all the way across the trait. So you can compute something called item information in CFA, although it's not strictly necessary. So in item information, the formula is the unstandardized loading squared divided by the error variance. I didn't bother to teach you this. I think it's in a slide, but I never mentioned it, because you can look at the standardized loadings and get the same information, basically. How good an item is relative to another item is conveyed by the standardized loadings. But you can compute the amount of information that an item has with this formula, unstandardized loading squared over error variance. If I were to plot what item information looks like, it's constant over the trait, because this scale is linear over the trait. This model, excuse me. I can convert reliability out of information, where the test information is the sum of each item's information. So information over information plus 1 corresponds to reliability. This is what I always do for people in explaining what these models mean for reliability. No one knows what test information means in terms of a scale. 4, test information corresponds to a 0.8 reliability. So in the sense that if you have a linear model, like you have in CFA, that corresponds to an item information function that is flat. So in this case, because the red item is flatter, its loading is lower, it contains less information than the blue item. But the blue item is better than the red item all the way across the trait. Information is flat in CFA. So if an item is good, if an item is better than another item, it's better than another item regardless of who you're talking about. These nonlinear curves in IRT, though, their information functions follow their shape. So I plotted the purple ones here. This is their item information function. They both peak at the location where their B is. So they have a B of 0, Therefore, they're most informative at a theta of 0. Pink is more informative than purple because pink has a stronger discrimination. So you take each of these item information curves and you literally sum them up, and that gives you something called test information. And test information can have any kind of funky shape. It depends on how many items you have at all these different points. So this makes it a little more concrete how this idea of a nonlinear model translates into an item not necessarily being good for everybody. These pink and purple items are best for people within this range of theta. They are not helpful for super high or super low people. If I had plotted these blue items over here, they would have a maximum information at their B value, which would be over here instead. So the blue items are most helpful for people over in this region. So that means that there's not going to be a single number that we can say my reliability is blah. Like my omega is 0.9, the end. Or my alpha is 0.8, the end. In these models, reliability varies as a function of the trait. So the only way that you can characterize reliability is to say over what range of the trait you have adequate reliability. And so that's what we'll get to look at next time. The questions. So just to keep you from getting too scared before you go, do you know what it's going to take to run these models in M+? One more line of code than you already know. The words categorical are. That's it. Pretty sweet, huh? Yeah. Yes.
So, is there any rule of thumb of items? I think it's like roll up and which value?
No, I don't think there is. There's just test information because it depends on how many items you have and where they all go. You can, if your item information is low, you can compensate by having more items. So it really just depends on how many items you think you can get away with to maintain adequate sensitivity at the regions where you care. So, all right. Other questions? All right, then I will see you Wednesday. Let me know if you need anything before then. Office hours are going to start now.